Hey everyone, I'm here with a video that will introduce the notion of reduced row echelon form, which I will often abbreviate RREF because that is a mouthful and a lot to write. And so this will be the idea of basically doing our Gaussian elimination using our row operations, but first dealing with matrices, which represent our linear systems, and then going a little bit farther so that we can just very quickly and easily read off our solutions. All right, so we're going to start with this example here, and basically we're going to just go through our usual process of Gaussian elimination, and we're going to use that to solve this. But then we're going to see that if we had gone actually a few more steps of reduction, basically a few more row operations, then we actually could just read off our answer directly instead of having to back solve. So first, let's just translate this into an augmented matrix form to make our lives a little bit simpler. So I'm going to make little matrix here with my bar. So I'm going to do my x1 column first. So again, you're just looking at the coefficients, plucking those off. So we've got 1, 2, and 4. Our x2 column comes next. We've got a 1, 1, and -1 there. Our x3 column, we've got a -1, 3, and 2. Then we put that bar there for where the equal sign is. And then after that, we just put the numbers that those are equal to, so 5, 2, and -1. So this is our augmented matrix representing this system, just keeping track of the coefficients and knowing our variables just by which column something is in. In terms of reducing, we basically want to get rid of this stuff, right, to get into like a triangular form. And so the first thing we might do then is get rid of our 2 and 4 below this 1, right? Basically zero out the rest of our first column. So the first thing I'm going to do is row 2 minus 2 times row 1, and simultaneously do row 3 minus 4 times row 1, a couple of replacement operations. So this is what we should end up with after that step. And then there's one more thing we want to get rid of. It's this -5 here. And in this case, we can use like the -1 right above it. And so we will do row 3. Now we don't want to add 5 times row 2. That would add -5 to get us -10. So we will subtract 5 times row 2. And this is what we end up here. Now we have our beautiful little triangle in this case. And so we can fairly easily read off solutions, right? So this last column, or sorry, the last row is reading as -19x3 is equal to 19. And so this tells us that x3 is -1. Once we know that, we can go up to the next one, get -x2 plus 5 times our -1 equals -8. So this means -x2, that's -5 added over is -3, so x2 is 3. And then after that, we can plug into our first row and get the x1 plus our x2, which is 3, minus our x3, which is -1, is equal to 5. And so that's adding 4. So subtract 4 over, and x1 is 1. And so this tells us that we have a solution, 1, 3, -1. So it's not too bad, but it turns out, well, especially if you have like a ridiculous number of equations, then this back solving could be a pretty long process. Also, in terms of like automating things, if you're utilizing technology, just doing a few more row operations really isn't going to take much time, but it can make it much easier to read off a solution. So what do I mean by this? So basically, our goal of this so-called reduced row echelon form is that we will be able to read off our solutions directly. So what I mean by this is we will have some form of our matrix where we can just very directly go, oh, x1 is something, x2 is something, and x3 is something else, just directly from that form instead of having to go through this back solving process. So essentially what we want is for each of our variables to be alone in their rows. For instance, you don't want the x2 and the x3 in row 2, you want just row 2, so you can read it off directly. Additionally, we can actually start with this -19 issue, right? So we had -19x3 equals positive 19, instead of dealing with that, right, the way we solve for x3 is you divide by negative 19 on both sides. You can actually do that as a row operation. So I'm actually going to start with the same form that I had up above and start working from there. So basically the first thing that we're going to do here is do one more row operation. We're going to scale and multiply by negative 1 over 19, or divide by negative 19. That will change our last row to 0, 0, 1, negative 1. And now we can just directly read off x3 equals negative 1 from that row. So now our next issue is basically, okay, here's my x2. The problem is I have a minus 5, x3 equals 8. I want to get rid of my x3 there. So the way that I can do this, and I actually want to get rid of my x3 in my first row as well so that I can eventually isolate x1, is I'm going to make these 0. That basically gets rid of x3 in the other two equations so that we can start getting down to just having one variable per. And so the operations that we will do here are row 2 plus 5 times row 3, basically using that 1 below to zero this out, and row 1 plus row 3, so that the negative 1 and the 1 cancel. So that gives us this matrix. And so again, our last row, we can quickly read off x3 as negative 1, but now we've also fixed our second row so that we can very quickly read off x2 is equal to 3, because there's a 0 in my x1 and x3 columns. The problem is still this guy now, right? So in my first row, I have like an x1 plus x2 is 4. I still have to think and back substitute that x2 equals 3. So I'm going to do one last row operation, and I will do row 1 minus row 2, basically to cancel that 1 out. And our final form, our reduced row echelon form, that's what this step is here. We can directly read off now. x1 is 1, x2 is 3, and x3 is negative 1. And so from here, right, in this case, it's not a triangle, but actually just like a straight up diagonal only, and we can just directly read off what each variable is equal to. So this is basically going to be the goal of a reduced row echelon form. We may not always be able to eliminate every variable. In those cases, we'll have infinitely many solutions, but we'll still be able to read those off very quickly, and we'll talk about that later in the video. Okay, so here is the formal definition of reduced row echelon form. And so I'm going to try to break down everything that we see here. So the first thing, and this is usually just kind of a simple matter, is if all of the entries in a row are 0, then that's true of any row below it. So basically all 0 rows here just go at the bottom, okay? So you can just throw those at the bottom, and we can always do that, right, by using interchange. We can switch rows so that all of those guys go at the bottom. The next part is where we encounter a really, really important definition, which is this leading entry. So when you're going across a row, we just kind of go left to right as we normally read. The first non-zero entry in a row, so second row, right, I hit my first non-zero entry here, third row, first non-zero entry here. These are our leading entries. Another name is a pivot. I guess because they're quite pivotal, they are like the really important thing that the reduced row echelon form and reading off our solutions kind of revolves around. So all of these pivots must be 1. And that's basically so we can just read off, right, like x1 equals stuff. In this case, x3 from our next pivot equals stuff. And then x5 equals stuff. Now, reduced row echelon form works for any matrix. It does not have to be augmented. So like this one, right, there's no bar, so it's not an augmented matrix. But if you had a bar, before this or before this, also totally fine. All of the same rules apply, okay? So then the next thing is that the leading entry in any row is to the right of the leading entries in the rows above it. So notice we start in the top left, and then we go down and right, and then we go down and right. We will always do that, okay? And so always think we're working, especially when we're like actually reducing and doing these operations, you work top left to bottom right. And so that's why we get all of these zeros kind of down below here, okay? So then the last thing, and this is a really, really important one, is that these pivots should be the only non-zero entries in their columns. So if you look at our three pivots, they are the only non-zero entries in their columns, respectively. Whereas, like these two guys or these three guys could all be non-zero potentially, and they might not even be 1, right? I could have like 2, 3, and 4 here or something like that. Would be totally fine because they are not in a pivot column. So those columns, they can basically be whatever they want. I did want to show a little screenshot here, and you're doing it for your intro assignment too, but you can use Sage to do reduced row echelon form. We are going to focus on doing things by hand early, but you can always check yourself. And so for that one we did earlier, this is the augmented matrix we were dealing with for that system, and it doesn't do augmented, so you can pretend there's a bar here and here. And sure enough, right, we can read off this first line as x1 equals 1, x2 equals 1 for the second, and then x3 equals -1 there. So we had the right reduced row echelon form. So here I want to look at just some examples / non-examples, or if it's a non-example, talk about how we get it in reduced row echelon form. So the first thing you should always do is look for pivots. Okay, so look for those leading entries, those first non-zero entries in a row. So here, first row, second row, third row. First row, second row, I don't get a 1 until over here, and then here, and then this one, and our third row has no non-zero entries. Okay, so there are my pivots. And then we just want to see, do all the rules get satisfied? So here, all my pivots are 1, but I got some problems, right? Like I want my pivots to be the only non-zero entries in their column. They are not, right? I need these to be 0. And so you would have to do some replacement row operations to make that work. So use replacement. I'm not going to do that here, but you would just need 3 replacement operations and you can make those all 0. This one, the pivots are all 1. They are also the only non-zero entry in their row. The issue, right, is here. I need to do an interchange because I need that bottom pivot to be to the right of the one above it, not to the left. So again, you're kind of creating that triangular form, or in this case, actually just like a diagonal. And then last but not least, this is fine in terms of like the left to rightness. It's also fine in terms of the only non-zero, but this guy needs to be 1. And so use scaling, just do times 1/2, right? So basically, you can always get to reduced row echelon form by using these row operations. All right, so for this first exercise, I don't want you to actually like go through and find reduced echelon form on your own or read off a solution. Your goal here is simply to determine whether or not each of these matrices is actually in reduced row echelon form or not, and then briefly explain your answer. So if you think it is in reduced row echelon form, why? And if not, what went wrong, right? Which of the conditions was not satisfied? So the last thing I want to talk about here is how to read off a solution. So I know I did it for that one example. This one is just a little more complex because it's not just 1, 1, and -1. So this is, first of all, in reduced row echelon form. So we should check that. Got my pivot, another pivot, and another pivot, right? My first non-zero entry in each row. When I look at their columns, I see all zeros except for that 1, 1, and that looks perfect. I have no rows that are all 0, nothing to worry about there. So the key, right, being that these are not pivot columns, so I don't really care that these are 2 and 3. Okay, so how do I read off a solution? Well, it's just translating back. So because I see the bar here, this is augmented. These are like my equal signs, right? So this is like x1, x2, x3, x4 equals, and then we just have our numbers on the right-hand side. So we can just translate. x1 plus 2x3 is 2. x2 plus 3x3 is 3. And x4 is 2. So notice we're not going to be able to solve for everything here, and that's because we don't have a pivot in every column. So basically, x3 is the important one here. This is what we call a free variable. So I know I mentioned this in class with our last example when we were doing our Gaussian elimination, where we weren't able to find what z was, and so we wrote everything in terms of z. We're going to do the same thing here. We're going to write the others, x1, x2, and x4, in terms of x3, because we're not going to be able to solve for it. And so when I do that, what happens? Well, I can just move this over to the other side. So x1 is just 2 minus 2x3. x2, do the same thing. It's 3 minus 3x3. x3 is just, well, itself. So x3 is x3. And x4, I don't need an x3 because x4 is just always 2. And so this is my solution set. And again, note that this means there are infinitely many solutions, one for each value of x3. Okay. All right, so here's your second exercise. So here I want you to actually go through the process of putting this in reduced or echelon form. So I want you to start by writing the augmented matrix. Again, just kind of get used to that more concise way of going through this process of Gaussian elimination. And then actually work all the way through to reduced or echelon form. So don't just stop at triangular form and back solve. I want you to go all the way to reduced or echelon form. You should be able to read off your solution directly, and just make sure you're showing your work. So make sure to label your steps with something like, row 2 minus row 1, or, row 2 times 3, something like that, so I know what's going on. All right, and our last exercise here should hopefully be a quick one. So I'm actually giving you the reduced row echelon form of a linear system, and just for consistency's sake, let's just call these x1, x2, and x3 as our variables. And I want you to use this reduced row echelon form to write the solution to this system. And this one is one that may require a little bit more work to read off because there are infinitely many solutions here. That's all I've got. Thank you very much for watching.